In this lecture, we're going to use the collision coalescence model that we developed before. dr by dt is equal to the difference in the velocities of the collector droplet by the collectee droplets times the liquid water content times the efficiency of the collision coalescence mechanism divided by 4 the density of liquid water. We're going to use that model in order to add an updraft to this cloud to make it more realistic. And what we want to do is we want to develop an equation that shows the droplet size as a function of height instead of the droplet size as a function of time. And the way that we're going to do that is to use dr by dt is equal to dr by dh times dh by dt. Of course, the dh's would cancel and makes this equivalent. But the height of time of the droplet as a function of time is just going to be equal to the updraft velocity w minus the fall velocity of your droplet. So if we substitute that in, so dh by dt is equal to w minus v, then our dr by dt is equal to dr by dh times w minus v. We'll take that dr by dh, which is, take this quantity, which is equivalent to dr by dt, substitute it into here, and you'll end up with a dr by dh equation, which is v1 minus v2 times the liquid water content times the efficiency divided by 4 rho L times the difference between the updraft velocity and the fall speed of the droplet. And we've been making this assumption quite a bit that v1 is much, much greater than v2. In that case, this equation is approximately equal to this. And recall, of course, that the terminal velocity of the droplet is a function of radius. We have these 3 equations here. When the droplets are small, the fall speed is a function of r squared. When the droplet is a mid-sized droplet, all the way up to drizzle droplet, it's proportional to r. And when it's a large rain droplet, it's proportional to r to the 1/2. And so, of course, when our terminal velocity is less than our updraft velocity, our droplet will actually be ascending above cloud base. When our terminal velocity is equal to the updraft velocity, at that point the droplet will be suspended in the air, will no longer be moving up or down, it'll be at the top of its trajectory. And when our terminal velocity is greater than the updraft velocity, then that droplet will then start to fall and will eventually exit the cloud base, exiting at the lifting condensation level. And of course the droplet is growing the entire time that it is moving. Regardless of whether or not it's moving upwards or moving downward, the droplet is growing because we know that dr by dt is always going to be essentially positive in this model. And so we start off with a relatively small droplet, and as it ascends, it starts collecting droplets, and it will continue to grow until some point when its terminal velocity is equal to the updraft velocity, and then it will start to decrease. It will start to descend, and it will continue growing until it exits cloud base, and at that point it will begin to evaporate all the way down to the surface. But at this point its fall speed is probably 8 or 9 meters per second, and it won't take that long to get down to the ground, but it will be evaporating on the way down. So the question that I have is, how can we identify the travel time of this droplet from cloud base to the top of its trajectory? And it's really a 2-step problem. The first is we just assume that at the top that our terminal velocity is equal to the updraft velocity, and we solve for the radius that will occur at using one of these appropriate equations for our drop size. And then we can use the dr by dt equation with our initial droplet size at cloud base, our droplet size at cloud top, and then we can, since we have those 2 quantities known, the only unknown in this entire equation is going to be the time, or the delta t. And that'll give you time from here to here. If you wanted to, so then the next question that we might want to ask is, how can we use this equation to identify the droplet size upon cloud exit? How big will that droplet be once it exits that cloud? And once again, you start off in the same way, in that you let v1 is equal to our updraft velocity, and you solve for the radius at the top of the trajectory. But this time you use the dr by dh equation, and you have your initial and final, or initial radius and the radius at the top of the trajectory. And this time you can actually solve for delta H. How high above cloud base will that droplet reach a terminal velocity that's the same as the updraft velocity? So now you know delta H, and you can redo this equation, dr by dh. This time you know the radius at the top, you know delta H, and you can use that to solve for the radius when H is once again equal to 0. Because we defined this coordinate system with 0 being cloud base and positive moving upward. And so you can use that equation to actually get the radius of the droplet as it exits the cloud. And then, if you wanted to see how fast that droplet would evaporate, you go back to your growth by condensation equation, and in this case, the relative humidity is going to be less than 100%, or the saturation ratio is going to be less than 1, and that droplet will evaporate, and you can keep track of how long that droplet takes to reach from cloud base to the ground, and you can determine the size of that droplet once it reaches the ground as well. So hopefully this gives you a schematic of how to use these equations to be able to answer difficult questions about a droplet that's in a realistic environment for the cloud that has an updraft velocity. And of course, the higher the updraft velocity, the higher that droplet will ascend, and the larger that droplet's going to be when it exits the cloud base, because it will have spent longer in the cloud and ended up collecting a lot more droplets both up and down in its trajectory. So one of the things that we really want to understand to look at how large cloud droplets, how rain droplets form in these clouds, it's very helpful to have a very deep cloud, and the only way to get a deep cloud is to have a very large updraft velocity.